Stanford University.
Have you ever wondered how a CAT scan is able to generate a three-dimensional image of your organs? These images are made using a process called tomography. In this technique, two-dimensional images are taken at several angles. Each angle gives us new information about the object. Next, an algorithm can combine all of these 2D images. The end result is a 3D image, or what's called a reconstruction, of the original object. Recently, this process was applied to tiny objects much smaller than the human body. Here are images of nanoparticles where you can see individual atoms in 3 dimensions. Just like a CAT scan, these nanoscale tomograms provide information about the object's structure. But what if we wanted to see how light interacts with one of these nanoparticles? Take solar cells. To design a better cell, we need to engineer not only the structure of the cell, but also how it interacts with light on the nanoscale. We need a tool to visualize these interactions. The technique we use is called cathodoluminescence. If we take a nanoparticle in an electron microscope and shine a beam of electrons at it, it can actually emit light. This light is called cathodoluminescence. Now, if we collect this emitted light, we can map out the optical properties of the object with nanometer scale resolution. Let's see what this actually looks like. Here is a tiny nanoscale crescent, made from a polystyrene sphere coated with a gold shell. If we excite this crescent with an electron beam in the electron microscope, we discover that it emits light in a few different ways. First, we find light emitted from the gold shell. We also find that light is emitted by an optical resonance at the top, near the tips of the crescent. These 2D maps show how light interacts with the structure with extremely high resolution, down to only a few tens of nanometers. But these 2D images only tell part of the story. Imagine trying to identify a person just by looking at her shadow. It would be quite a challenge. To push this technique into the 3rd dimension, we combine cathodoluminescence with tomography. Remember that tomography requires a tilt series of 2D images of the object taken at different angles. So, we tilt the crescent and take 2D cathodoluminescence images at 14 different angles. Then, by using tomographic reconstruction algorithms, we can generate a 3-dimensional map of how light interacts with our nanoscale particle. Here's a cathodoluminescence tomogram next to a structural tomogram like the one we saw earlier. The cathodoluminescence tomogram shows us what parts of the crescent light up under the electron beam. Using information about the color of light emitted, as well as what part of the particle is emitting, we can make a different kind of 3D reconstruction that helps us visualize this particle in a new way with nanoscale resolution across visible and near-infrared frequencies. So, to recap, we have combined cathodoluminescence, a technique for probing optical properties of nanoscale systems, with tomography, a 3D imaging technique. This has allowed us to generate the first 3-dimensional images of the radiative optical properties of a nanostructure. To learn more about this new technique, please see our recent article in Nature Nanotechnology.
For more, please visit us at stanford.edu.